Good evening, and welcome to episode number 14. Today, we'll be investigating how to estimate your economy. So, how do we estimate an economy? And why do I say estimate? Well, there's no real physical way to basically determine what these two main parameters are, those being the total time it takes to build your bridge and the size of your build team. There's no way of really knowing what these are ahead of time, not like with the efficiency score where we could directly get those things out of SAP. With the economy, what we're going to need to do is basically construct a number of economy models, essentially is what I'll call them, in order to estimate what it should be. Now, I've developed a couple of models here, and basically the first place where you're going to want to start is first get some sample data. Now, I've just taken some of the results from the 2014 National Students to Bridge competition. I have the number of schools, the total time for their build in minutes, and the economy score. Now, I've only gotten data more specifically for the top three schools, Berkeley, Davis, and MIT. And pretty much what I've done is I've estimated the number of builders on each team, the number of runners, the number of bargers, the number of members, and the number of bolts for each bridge. So you can go ahead and either go to YouTube or look at pictures and kind of just figure out what those numbers are. Unfortunately, there's not a lot of videos out there, but anyways, so the main models, the four ones that I'm going to look at first are just very simple linear regression models. And kind of going back to your Stats 108 class, hopefully you recall that how you go about constructing linear models is basically doing some kind of single variable regression, or in this case we're going to be looking at multivariate regression. So how do you do a multivariate regression on this data once you have it? Well, the best thing to do is just to use something that already implements doing that kind of analysis for you. And MATLAB has some very nice tools in its own repository that do this in a very simple call to MVRegress, which is just the general multivariate or single variable regression. So I've included basically as column vectors the main independent variables that I want to basically get constant coefficients for, and I've also included my observations, my economy score, in a column vector as well. So you can place basically whichever independent variables you want to get coefficients for into basically a matrix, which each column of the matrix corresponding to each independent variable, call it x, plug it in here as the first parameter. The second parameter is just your column vector of observations, or your economy score. So I've done that for basically the first three models, and I'll kind of take a look at what some of those are doing. So the first model pretty much just has a coefficient multiplying the number of members. Second model has a constant coefficient plus a coefficient times the number of members, and then the third model pretty much has constant coefficients multiplying the number of members and the number of bolts here and here. So how good of results do these give? Well, model number one is actually pretty abhorrent comparing it to the actual results. So you can see it doesn't do a very good job of predicting what the economy score should be. And partially that's in relation to the fact that it's not even taking into account the number of volts, nor is it even really considering the number of builders that you're using for each build. So model one's not that great. I wouldn't use model one, but it's actually the model that Danny Savannah had used, just to give some context. So model number two, a little bit better, you can kind of see based on the results here, but basically, again, it only works in a sort of a limited range, since you have to have this constant coefficient here. There's no way that if you scaled this down to near zero members, it would still be costing this much. That just wouldn't work. And likewise, again, it doesn't account for the number of bolts. So model number three is probably maybe the ideal model that I would suggest, at least based on the linear regression models, numbers 1 through 3. And basically, it linearly scales with the number of members and the number of bolts, very intuitively. So the members obviously cost more than bolts, And they give actually reasonably good results, just kind of comparing these. So if you wanted a really quick and dirty estimate, I'd say create a model, fill out the rest of this table a little bit more and get a few more observations, and then pretty much maybe go with something similar to Model 3. Now, Model 4 is not quite a linear regression model, but I'll kind of demonstrate how I got it. I'm essentially using sftool, which is a surface fit tool. And just running this script really quickly, you can pop up with the surface fit tool and specify, basically your two main inputs. Again, surface fit only works with two main independent variables. So that will be, for me, the bolts and the members, with the output or observations, Z being the economy score. Now it'll automatically do the interpolation. You can specify like a polynomial fit, and it will exactly interpolate it using a surface because there's only 3 points. If I had more points, it wouldn't exactly do this. But you can get your coefficients pretty much. It'll spit out what the equation should be from that. But the problem with this is that the coefficients are kind of non-physical here. You have negative coefficients multiplying the number of members and bolts, which doesn't make sense at all. Because, if you're going to increase the number of members in your model, you expect the cost to go up, but in this case it doesn't. So just be wary if you see things like this, and this is kind of why I bring up Model 4, is that partially if you don't have enough data, then you can run into problems like this. If you're trying to fit more independent variables than you have, or I guess more coefficients than you have observations. So very dangerous. Just be wary of this. If you start to get negative coefficients, that's probably a bad sign. Now, it's very deceptive because the results are actually quite good. In fact, they're pretty much spot on, but that's just because the plane is going straight through all those points. So pretty much models 1 through 4 are what are called empirical models, and that's basically just kind of taking the end result, the observation of whatever the physical process is, and then trying to link it to the independent or physical variables as inputs. And that's the whole goal of linear regression. However, there might be another method that you might try, and that's basically a simulation of the actual physical process involved of performing a construction run. Now, I've implemented a very simple simulation of what a construction run might look like in a MATLAB context. And basically, I'm taking as input variables all of these things, and I'm associating with certain times taken to do certain activities in the model, and using these pretty much to systematically come up with a way that hopefully simulates what a construction run might look like. Now, you don't need to know how the actual construction works, or the simulation works, rather. But it's useful to kind of see what the output looks like. So in this case, I'm just going to really quickly go to my MATLAB command prompt and then kind of go to maybe a previous call of the construction function with the input variables of the number of runners, the number of bargers, the number of members, and the number of bolts. And when I execute this, it'll spit out pretty much an estimate of what the total time should be for that bridge. In this case, it's the Berkeley Bridge, and the time is fairly comparable. It's about 8.5-ish, which is reasonably close to what this is. And you can actually see, just kind of looking at these numbers, they're decent approximations of what these numbers are. So I was able to achieve these results basically by calibrating the model. You don't necessarily, again, need to know how that happened, but basically I kind of have an additional script here that went through and calibrated the model and based on pretty much my input data, just for those 3 model runs, Berkeley, Davis, and MIT. And then essentially, hopefully, I'll have what results is a simulation model that will be able to predict not only good scaling with the number of model members and bolts outside of the range in which I was looking to define the model and calibrate it, but also define it based on the number of runners and bargers. So this could be potentially very useful if we were trying to, who knows, estimate once we have a completed bridge what our build team should look like, how many members we should have. So, that's pretty cool. Hopefully that's useful. This is probably the most complex model. It requires that you run a MATLAB script to do it, but, if you're not averse to maybe doing that, then this could be maybe the most robust. Otherwise, again, I'd say Model 3 is probably the best quick and dirty model. It's the one I use. It's probably the one that Quincy used. And I'll just kind of quickly show you the results of doing, relating these models to basically the example design we've been working on in the past few lessons. So I've estimated kind of the number of builders, runners, bargers, members, and bolts for that particular model that I constructed, that example design, and here are the results. So if you can see, there's some pretty variable numbers here. But they all fall within a reasonable range. And assuming you use the same model to compare your results, then it shouldn't matter too much which model you pick, just as long as you're consistent with which model you choose. Just choose one and then use it for all your analysis. Alright, well, I know this is probably a lot to take in. It's a pretty complex subject, but hopefully you'll be a little bit more geared towards figuring out which kind of model you want to use and then estimating your construction economy score. If you have any questions, please feel free to ask. In the meantime, I'll see you guys later.